what do we do with these theta hat stars over here? Well, it would still be pretty interesting by the same reasoning to calculate the mean of them and to calculate the standard deviation of them and to calculate their distribution. For example, by making a histogram and so on. And all three of those turn out to be quite interesting, and Efren was able to show that. And in fact, perhaps the best way I can show you what I'm talking about is to, in fact, take you to something that I was working on just yesterday with the class I'm teaching up at Santa Cruz. So I'm going to go to a different web page than ours, and then this is a reminder to me to next time to put this stuff on our web page. So I'm teaching a class, I think I've mentioned to you, for my sins, I'm teaching a class now that's meant to be non-Bayesian called Intermediate Classical Inference, Classical Meaning for Quantists. And we've just been talking about the bootstrap in there. So let's go ahead and grab this code here. And I will tell you about what's going on. So people are often working with data that's strictly positive. And as long as the mean is far enough away from zero relative to the standard deviation, people sometimes find it useful to model strictly positive data as draws from a normal distribution. Even though you know the normal distribution could, in principle, get values that are arbitrarily far in the left tail and go negative, it will happen with very small probability if the mean is a lot larger than the standard deviation is. So here I've made a little data set that has 10 observations in it where the data generating mean was 100 and the data generating standard deviation was 30. And I pick a normal random sample of size 10 with those mu and sigma values, and I sort them from smallest to largest and round to the nearest one figure behind the decimal point and stick that into a vector called y. So here's my data. And if you look at maximum likelihood in this simple Gaussian model, the MLE maximum likelihood estimate of the population mean in the population we're trying to generalize to from the y vector is simply the sample mean, which came out 92, a little bit fairly close to the 100 that was the data generating number. And the MLE of a standard deviation is a little bit different from our ordinary thing that we would get in R by typing the SD command, because the MLE turns out to involve adding up the sum of squared deviations, yi minus y bar squared and so on. But instead of dividing by n minus 1, the MLE says divide by n. And so you can do that readily in R code by simply asking it to compute the squared discrepancy between y and its mean, and then take the mean of those square discrepancies. That'll be your 1 over n average, and then take the square root of that. So the MLE for the standard deviation comes out about 36, and that's, again, not too far from the actual data generating value. And then if somebody's interested in the coefficient of variation, the population value is what you get by taking sigma over mu. So the coefficient of variation is a measure of how big the noise is in the actual data generating process relative to how big the signal is. And so a natural way to measure that in Gaussian families is to compute sigma over mu, which here is 0.3. And the MLE for that, by what we talked about earlier this quarter, what's called functional invariance. If you know the MLE for mu and you know the MLE for sigma, you can just take the appropriate function of those things and get the MLE for this function. So I just take the sigma hat MLE and divide it by the mu hat MLE, and the estimate turns out to be about 0.39 on this data set, which is a bit bigger than the 0.3 that's the data generating value, and that's largely because, well, it's two circumstances. You see how the sample standard deviation in this data set came out a bit bigger than the data generating value, and the sample mean came out a little smaller. And so overall, this number is a bit higher. And now I wrote a little bit of code to do the bootstrap for us. There's R code that does the bootstrap for you, but I wrote some homegrown code to do it to show my students how to do it. And so let's go ahead and run this code. So I'm going to need a new copy of R. So let's look again at what the code does. It says, all right, I'll pick a large number for capital M, like 100,000, and I'll create a vector of missing values of that length that I'm going to fill with these theta hat star things. And then I just loop. As j runs from 1 to m, I sample the y vector of size little n with replace equals true. That creates an IID sample, just like the bootstrap idea says. And then I calculate the mean of this y star data set and the standard deviation and calculate the theta hat. And I fill that into this vector called theta hat MLE star. And then every 10,000 iterations, I write out the iteration number to make sure that I don't have to wait forever for this to see how long it takes to run. And then at the end, I'm going to make a histogram, and I'll also work out the mean and the standard deviation. So what I've just written is code that does exactly what we just agreed you should do in this picture. I start with the data vector, which has 10 numbers in it, and it has a sample coefficient of variation, theta hat. I take IID samples of size 10, 10,000 of them, or 100,000 of them, capital M is 100,000. I get these bootstrap data sets, which I called y star each time, and then I get a theta hat star from each y star, and I collect them together into this vector over here, which in my code is called theta hat MLE star. Now, all three of these things are interesting, the mean, the SD, and the distribution. So let's go ahead and run it. What code did I run already? I ran nothing already, so let's go ahead and run all the code all the way down to finishing drawing the histogram. And I see that I forgot to, over here under miscellaneous, I forgot to turn off the buffering. It would have written those things out for me in real time. So there's the bootstrap distribution of the MLE. And I'll draw some other things in. I'll draw, for example, I'll draw the actual MLE value in as a vertical line. And while we're at it, I'll compute the mean of the theta hat MLE stars and the standard deviation. All right. So the mean of this picture that you see here, does it seem to land right on the red vertical line or a bit to the left or the right of it? Seems to land to the left of it. In fact, I just worked out its value was about 0.354, whereas the MLE was about 0.38 something. Let me type out theta hat MLE for you again. Theta hat MLE was about 0.39. Efren was able to show that the amount by which the mean of these theta hat stars fell below or above the single point estimate you get from the data can be used to correct the bias of the MLE. In other words, this number, 0.354, is coming out a certain distance below the actual value, so we could compute 0.354 and see how much that falls below the single point estimate. And it's about that much. And that's telling us that the MLE is biased on the low side in this data set by about 0.031. And so to get a better estimate, bias corrected MLE for theta, I should take the theta hat MLE and add to it that bias term, which I got by subtracting the mean of the MLEs. Now let's see what I do. Yes, I did the mean of all those guys. I subtract mean of theta hat MLE star minus the actual theta hat MLE. Isn't that how I did that? So basically, I just lay off the same amount going on the other side, and that's going to get a bias-corrected version. And so what is that? Oh, I didn't do it right. Mean of theta hat MLE star. Oh, maybe there needs to be a minus sign there. There we go. And so to correct the bias, what I should do is I should find how far that vertical red line is from the mean and see how big that is and move onto the other side of the mean that same amount. And so this turns out to be theoretically a good way to create a bias correction for the MLE. Moreover, the standard deviation of these theta hat MLE stars turns out to be a good so-called non-parametric estimate of how much uncertainty we actually have about the theta hat MLE as an estimate of theta. So looking back at this diagram again, this number here helps with bias correction of the MLE, theta hat. This number here leads directly to an estimated standard error of theta hat. And moreover, notice, look at the nature of the diagram. Usually in the version of this that involved working with the population part of things over here, in order to make the MLE machinery move forward, we have to make a particular assumption about the parametric form of the population. Does it appear as though we had to do that anywhere here in this diagram? Did we make an assumption that the data were draws from a normal curve or a gamma or some other parametric family? What's it look like? No. So this is actually a frequentist non-parametric technique. And in fact, it leads directly to an estimated standard error that's a non-parametric estimated standard error. And you can compare that with the standard error you would have gotten if you had the right parametric model, and it will turn out to correspond roughly to the standard error from the right parametric model. But if you worked out the standard error from the wrong parametric model, they won't be the same, and to the extent that they're different, the bootstrap number will be closer to right than the one that you got from the parametric model because it was wrong. So he's actually made a big improvement here. And then the final question is, this distribution, well, there it is. So now you're Efren, and you want to build a confidence interval for theta. Oh, sorry. Well, look, the horizontal scale is the same as the theta scale. It happens to be theta hat MLE stars across the bootstrap stuff. And so I imagine, and I've never talked with Brad about this to see what his motivation was, I imagine that one day he just said to himself, you know, that looks like a posterior distribution for theta, given the data set. And if it were a posterior distribution, what would be a simple way to build a 95% confidence interval? Quantiles. So I would go in 2.5% into the left tail of this theta hat MLE star distribution and pick out that number, and I'd go 2.5% into the right tail and pick out that number, and those would be the left and right endpoints of my 95% interval. And that, in fact, is what he first recommended in 1979. He called it the percentile method, the bootstrap percentile method for creating confidence intervals. And his justification of it was actually Bayesian. He had a two-step argument. Step one, good frequentist intervals can be computed by creating Bayesian posterior distributions with diffuse priors and getting percentiles from them. And step two, which turned out to be true. And step two, he then went on to argue, based upon theoretical properties of the multinomial distribution, that's the basis of the bootstrap, that this thing here I'm showing you here is in fact a good approximation to the Bayesian posterior distribution, at least when little n is large. Turns out that it's not necessarily so good when little n is small, as we could look at if we had time. I'll think about it in a minute whether we have enough time. So his argument now is, gee, that looks like a posterior distribution. So I'm just going to go ahead and go 2.5% in from the left and 2.5% in from the right. So I can do that either using homegrown software, like what I have here. So basically I just say, all right, bootstrap percentile confidence interval is what I get just by running the quantile function on those theta hat MLE stars and picking out the 0.025 point and the 0.975 point. And once I've done that, I can go ahead and plot all of them. And I get an interval that runs from about 0.195 to about 0.512. And so there's my bootstrap 95% percentile method confidence interval, arrived at by some sort of funny blend of Bayesian and Frequentist reasoning. And so one of the important steps in what he's doing, which turns out to be helpful for us as Bayesians, is that he claims to have just created an approximation to the Pasteur distribution with diffuse prior information. But he did it by resampling from the data rather than by resampling from the parameter vector. Think about how MCMC does it. Every time you run a new iteration for MCMC, you take another sample of the parameter vector. He's doing something quite different. He's resampling from the data, and yet he's able to get an approximation to the Pasteur distribution with diffuse prior information by resampling from the data. And the cool thing about that for using this idea to do approximate non-parametric calculations in the Bayesian world is that it's a lot faster to resample the data than it is to run MCMC, particularly in high dimensions. And so we can use this fact as a computational shortcut for ourselves. Now, there are other better methods. Yes, please. You're really asking a central question that helps to understand what's going on here. He said, is this something like searching in the data space? And of course, from a Frequentist point of view, you remember that is what they want to do, because you remember their whole idea was to think about other data sets than the one you actually got by imagining what the other data sets might have looked like. So we usually write down models of the form yi given theta are IID from some sampling distribution. Oh, thank you. Yes. IID from some sampling distribution, P of yi given theta, right? But from a Bayesian point of view, the definition of P of yi given theta is it's equal to the joint distribution of yi and theta over the marginal prior distribution. So I can write the joint as P of yi, P of yi comma theta as equal to P of theta times P of yi given theta. Now before, from a Bayesian point of view, before you saw any data, do you know what theta is? Theta is some population value that you're wondering about. Before you see any data, do you know what theta is? Well, no. And before you saw any data, do you know what the yi's values are going to be? Well, no. And so at design time for you as a Bayesian, this is a kind of joint predictive distribution for the data and the parameter. I should really write it using my general notation. I should actually write it, this thing here, given the background information. And it's a kind of a joint prior distribution for how the data is going to come out and also how the theta will turn out what the theta really is once we start looking at data. If you regard this thing as somehow the central object of interest, then the idea is as follows. The Bayesian idea is to learn about P of theta given y by perturbing theta in that joint thing. And the Frequentist bootstrap idea is to learn about essentially the same thing, because Efren is using a Bayesian argument to get his Frequentist confidence interval, but we learn about that thing by perturbing the yi's instead, by perturbing the yi's in this thing here. And so the Bayesian idea is to hold the y's constant and perturb the thetas in that joint expression, and the Frequentist idea is to hold the theta constant and perturb the y's. And if you do it right, a hand waving on my part should suggest that there ought to be something of common interest to both camps in doing that. Somehow you ought to be able to learn about the joint distribution either by holding the theta fixed and perturbing the y's, or by holding the y's fixed and perturbing the theta. And because MCMC is the perturbing the theta argument, and that tends to be slow, this is MCMC slow, and this over here is the bootstrap, which is faster, we can use this fact to find computational shortcuts, approximate Bayes shortcuts, by perturbing in the data space rather than perturbing in the parameter space. Cool idea. Now, Efren went on to write a series of papers after that over about a 10-year period in which he worked out improvements upon this. So actually, if you want to do bootstrapping, let me show you how to do it in R in simple settings. There's a function called boot, and there's a function called boot.ci, and you can get them both by loading the boot package from CRAN using the library boot command. And then what I do with this code right here is I write a function that calculates the coefficient of variation, in which you give it a data set, and it'll work out the coefficient of variation of that data set, the sample coefficient of variation. And then, but the function has to be set up in a very special way for the boot function to work. And then I run the boot function, and I say data equals my actual data vector y, statistic equals, and I name the function that I'm going to be trying to bootstrap, and then I tell it how many times I want to do it. And I use the symbol capital M, but the boot people use the symbol capital R for repetitions or replications or something. So you would have thought all I have to write for the coefficient of variation function is function of the data, and you just calculate the mean of the data and the square root of the mean of the variance, the square root of the mean of this blah, blah stuff, and then return the SD divided by the mean. But in fact, to make things ready for the boot function, you have to make your function have two arguments, and the first one is the data, and the second one is a kind of dummy argument for which indices amongst the data vector you're actually going to evaluate at. And so even though I don't manipulate that particular second element of the function, the boot function does. And what it does is it chooses random choices of indices at random with replacement from the numbers 1 to n, and then indexes your data vector with that, and that gives you a random sample, right? And so this is exactly the syntax you have to use to be able to use the boot function. And so I'm going to go ahead and bring this stuff in and run it, and you'll see it runs pretty fast, about as fast as my code did, maybe even a little faster. About the same. And look, it produces the same exact bias correction that I showed you before, about 0.0322. That's just about exactly what we were getting a minute ago. The reason we're getting slightly different numbers now is that the boot command used different pseudo-random numbers than I did when it was doing its random sampling. And so it's going to have slightly different numbers on that basis. And look, the bootstrap standard error is the same as the standard deviation of, apart from noise, is the same as the standard deviation of the theta hat MLE stars. So now, of course, you could make a naive confidence interval just by starting at the MLE and going roughly 2 of those standard deviations, standard errors either way. But that's going to be a symmetric interval when things ought to be asymmetric. And if you look at the picture automatically builds in asymmetry. Because if this distribution is asymmetric, then the interval is going to be asymmetric, as it should be. And you can produce an improved version of this interval by running a version of intervals called the BCA method. Efren produced a whole bunch of different improvements on the percentile method. And one of them, the one that works best, is called the BCA method. And so here I'm going to run a new, let's plot these results first. So the first picture it plots on the left is the same picture I showed you already. This is the bootstrap distribution of my coefficient of variation across the bootstrap replicates. And the little vertical line is the actual MLE value. And so you can see that there's bias that needs to be adjusted. And then this produces a normal QQ plot of those guys, which you can see doesn't look quite normal because it's got some stuff happening in both tails that's a little different from the normals. So now let's go, however, I'll get the fancier bootstrap confidence interval now by running the command boot.ci, that particular function. And it finds that it gets virtually the same exact percentile interval that I got before by homegrown means. And interestingly, the right thing to do to get a better interval using Efren's bootstrap approach is to take, it's not far from taking that exact percentile interval and simply shifting it to the right exactly by the amount that corresponds to the bias correction. So we just take it and move it 0.06 to the right, and that gives you pretty much what the BCA method is saying to do. So BCA stands for bias corrected and accelerated. And what I believe we've just learned on this particular data set is that the bias correction is substantial. and corresponds to what I did already to get the new bias-corrected point estimate. And the thing that he calls acceleration is not substantial, so we end up with pretty much the same story. And I'll tell you how he does it. Let's go back. I won't tell you the full details because it's tedious, but I'll tell you the basic idea of how he does it. So where's that code back here? So the percentile idea was to stick with this distribution here and go 2.5% in and 2.5% in from the left and the right, correct? That's what we were just doing a minute ago, right? What Efren showed is that you can get an improved interval, at least in small samples, by sticking with that same idea. So you don't have to mess with this distribution, but you use the data to determine what the right percentiles are. So you don't necessarily go into the 2.5% point and the 97.5% point. You go in maybe to the 1.8% point and the 96.9% point. And those two numbers are chosen based upon theory he developed in a JASA paper for how to make the interval have better coverage probabilities. So he says, don't mess with this bootstrap distribution, but instead of going right in 0.025 and 0.975, you can get a better interval by going in some other quantiles. And he has a fancy way of figuring out what those other quantiles are that you can read about in his JASA paper. Okay, so that's the bootstrap. Enough about it that we need to know for now in order to be able to continue reading what was going on in that other story we were looking at. So let's go back to that story. No, it's not that one, it's the other one. So let's go ahead and open this guy, which for some reason opens bigger than it should, but I know a way around that. So I'm going to try to use the Dirichlet process to construct non-parametric interval estimates of the variance, or equivalently the standard deviation of some population. And I've just introduced to you that one frequentist non-parametric approach is the bootstrap. And I mentioned a minute ago that the best bootstrap technology at present for non-parametric interval estimates is this thing called the BCA method. There's a computationally less intensive cousin called the ABC method that produces answers about the same as the BCA method, but quite a bit faster, and that matters on big data sets. So with only 10 observations, it all goes like lightning, but the ABC method turns out to be a computationally quicker version of BCA, and so you could use that instead. There's an idea called the iterated bootstrap. That actually made things even worse. So here's a little paragraph of bootstrap propaganda from the book that Efren and his student Tip Shirani wrote. One of the principal goals of bootstrap theory is to produce good confidence intervals automatically. Good means that the bootstrap intervals should closely match exact confidence intervals in those special situations where statistical theory yields an exact answer, and should give dependably accurate coverage probabilities in all situations. The BCA intervals come close to these criteria of goodness. That's right out of their book. They're basically saying, you give me any problem you want, and the BCA method is going to give you good intervals. Well, that's saying too much, it turns out, and now I'll show you an example. Let's take the log normal distribution. And the way you get the log normal is how? Anybody recall? Let's take the standard log normal distribution. So what do? Exponentiate the standard normal. So it should really be called the exponential normal distribution, but as I think I may have mentioned before, but everybody calls it the log normal and we're stuck with it. So obviously it has to have only positive values because we exponentiated something, and it tends to have an extremely long right-hand tail. The variance of that distribution is going to be hard to learn because the tail itself has a lot of influence on the variance of any distribution that's skewed. In fact, it has a lot of weight, has a lot of influence on the variance of any distribution, whether it be, if it's symmetric, the left and right tails together have a lot to do with the variance. So this is a highly skewed and heavy tail distribution. If Efren and Tip Shirani are right, then we ought to be able to use the bootstrap to get useful confidence intervals for the population variance. So consider the following model in which I'm going to imitate the basic De Finetti story, except I'm going to put all my eggs in the standard log normal basket. So if I knew what F was, the Y's would be ID from capital F, but then I'm going to pretend I know that capital F is exactly equal to the log normal distribution with parameters 0 and 1. And what that means is that if you take the logarithm of the yi's, they will have mean 0 and standard deviation 1. In other words, the 0 and the 1 refer to the mean and the SD not on the original data scale, but on the log scale. And suppose you can almost always write interesting things that you're interested in about the underlying CDF in terms of what are called functionals. So I work out the population variance in terms of the population mean, and this DF stuff is just a fancy way to talk about integrating with respect to the density. So there's the usual unbiased sample variance. So I calculate the sample mean, and I work out the sample variance from it. And it's almost the nonparametric MLE of that population variance. What you would get to get the nonparametric MLE would be to divide by n right here instead of n minus 1. And it serves as the basis of ABC intervals. You ought to be bootstrapping the sample variance if you want to learn about the population variance. That's what inference has to do. Okay, so let's see how things went. First of all, let's look at how the sample variance behaves. The right answer with the standard log normal distribution for the population variance turns out to be e to the e times e minus 1, which is about 4.67. So I did 1,000 simulation repetitions of choosing samples of size 10 from the standard log normal distribution and computing the sample variance each time. Because the sample variance is unbiased, unless there was something wrong with my simulation, this number here has to be really close to 4.67. And similarly for every number like that in that column, and it is. So that's good. And these things here are simulation standard errors, and they should go down with more data in each sample, and they do, because I have more observations in each sample. So you can see they go down in a monotone way. That's a good thing. But look at how different the mean is than the median in the actual repeated sampling distribution of the sample variance. The mean is much bigger than the median for small sample sizes, and even up to sample size 500, it's appreciably larger. Now, this is kind of interesting. If I look at the percent of the actual distribution when the sample size is 10 of the repeated sampling distribution of the sample variance that's below the true value, it turns out to be 77% of it is below the true value. And that number falls down toward 50% as we move towards symmetry, but not very quickly. And so what this says is that the sample variance achieves its unbiasedness, at least for log normal data, in an interesting and peculiar way. It achieves its unbiasedness by being too small most of the time and then much too large some of the time. And those two things balance out to get the unbiasedness that you might want if you were an unbiasedness person. And I show much too large some of the time by looking at the 90th percentile. The right answer is about 4.7. The 90th percentile is almost 10 for small values of n, and it's still quite big out there for n equals 500. And so, for instance, here is a histogram of the first 950 ordered values of the sample variance for n equals 10. And you can see that the repeated sampling distribution, it's supposed to have a mean of 4.67, and it actually does have a balance point right there. But it achieves unbiasedness by being rather too small most of the time and much too large the rest of the time. And so now this, like I said a minute ago, that does not bode well for the bootstrap, because we're using a summary from the data that is only achieving unbiasedness by this strange business of having two wrongs make a right. So here are the answers for how well the bootstrap intervals perform. We built 90% intervals. They were supposed to be 90% intervals using the BCA method. Actually, we used ABC, but it's the same as BCA pretty much. And look, you are giving people, you're using a method that claims to cover 90% of the time, and your actual intervals are only covering 36% of the time. This is an example of a frequentist method that's not performing well according to basic frequentist criteria. You told the world that, you, Efren and Tipshirani, told the world that your method, which is sitting there right in CRAN as a freeware that everybody should be able to use to always get very good confidence intervals. Your 90% intervals are supposed to cover about 90% of the time. With small samples, it actually only covers 36% of the time. And even with 500 observations, which sounds like a big sample from a distribution, the 90% intervals are only covering 77% of the time. So this puts the horse laugh to that paragraph earlier, right? The BCA intervals come close to these criteria of goodness. Well, maybe Efren and Tipshirani would say, except on a set of problems like the one you, Draper, just invented for the bootstrap, right? Maybe that's how they would patch that up. But the bootstrap is not working that well. Well, why not? It turns out that the mistakes, if you look at it, you work out the mean length and the median length of these intervals, and look at how the mean length is so much longer than the median length. And you look at the mistakes it makes. When it's entirely wrong, what percent of the time does it lie entirely to the left of the right answer versus what percent of the time does it lie entirely to the right of the right answer? So 61.1 plus 2.9 plus 36.0 have to add up to 100% because the intervals either have to be entirely to the left of the right answer or include the right answer or be entirely to the right of it. But look, with small sample sizes, the mistakes are almost always from the interval lying completely to the left of the truth, which makes sense because the sample variance is usually too small and then occasionally much too large to create its unbiasedness. Well, this is basically showing us what's wrong with the bootstrap. We are asking the bootstrap to do something that it's not able to do. And I showed this example to Brad once, and he said, oh, yeah, you can't use the bootstrap for that problem. It's too hard. So here's our log normal distribution. And remember, the log normal tail goes out a long way. Suppose I only have a sample size 10. Well, most of the points are going to fall right here, right? Because that's where the density is highest. So I'm going to see, a couple points there, and I might see 3 points there, and 2 here, and 1 there, and 1 there. 1, 2, 3, 4, 5, 6, 7, 8, 9, and maybe this one is right there. So what is Efren doing? He's resampling from these points here. When he's creating a new data set for the bootstrap to be based on, can he ever get a point out here with his bootstrap technology? No, because he's only resampling from the data he's seen so far. And so the problem with the bootstrap and problems like this is that it cannot give values in the bootstrap samples that are greater than the maximum y value, because by its very definition, all it's doing is resampling from the data. In other words, the bootstrap is entirely ignorant about the tail behavior of the actual distribution we're sampling from beyond the biggest value that happened to land in the data set. If you get a data set where that biggest value goes way out in the tail, then that's going to be good. The bootstrap will produce nice wide intervals then. But most of the time, the bootstrap will have, on small samples, will be based upon only what it's seen so far. And with only n equals 10, it hasn't seen the whole right tail yet. So there are really only two ways to fix this problem. Remember, the bootstrap is a non-parametric technique. It's not pretending that it knows things are log normal. It's just saying, what if all I know is that the data points fell here? Then what can I say about the truth back in the population? And it's in trouble with respect to the right tail. So there are only really two ways out, either for frequentist or for Bayesians. Actually, no, there's a frequentist way out and there's a Bayesian way out. And the frequentist way out could also be used by the Bayesians. Namely, you could either go parametric and try to assume a parametric model. And then look, if you assumed a parametric model, the parametric model would predict stuff out in the tail beyond what you actually see. And so you would inform the inferential engine about what's happening in the tail by the nature of your predictive model. Of your parametric model. That's one way to go. The other way is to be Bayesian non-parametric and teach the inferential machinery about that portion of the right tail that the bootstrap hasn't seen yet by putting in prior information about what that tail looks like. And in effect, parametric models do that, don't they? They do it through the sampling distribution, but you could think of it as another way of putting in prior information about how strong the tail is, because heavy tails are possible within the log normal family. And even with data that only fell here, the log normal tail would go further out than the largest observation. So two ways forward, and the Dirichlet process actually uses the second of those two approaches. It can be thought of as a Bayesian generalization of the bootstrap in a way that teaches the inferential machinery about the portion of the tail that hasn't actually been seen. So like it says here at the top of page 6 on this part 6, section 1 version of the organized notes, the bootstrap fails because it's based solely on the empirical cumulative distribution function. And I think I've told you what that is last time. You just keep track of how many observations are at the place you're at or below it. It's based only on the data vector, right? So it's based solely on the data vector, and the empirical CDF is ignorant of the right tail behavior beyond the largest value. So to improve, we have to bring in some kind of information about tail weight and skewness, either through a parametric model or by a Bayesian non-parametric model. And so the problem is solvable parametrically. I could pretend I knew somehow that the data really were log normal and put a diffuse prior on mu and sigma squared. It's easy to use Gibbs sampling to produce intervals now. And look, now having assumed the log normal model when the data generating mechanism really was the log normal model, and just saying I don't know what the mu and the sigma squared are in this model, the nominally 90% Bayesian intervals actually cover 89 to 91% of the time as a function of sample size. But to do so, they have outrageously large widths. Look, with a sample of size 10, the mean length of these intervals is 6 times 10 to the 5th. Because the log normal distribution, the log normal distribution, the standard one, actually the problem, well, this is a problem with the normal distribution that's not usually a problem. The normal distribution goes on forever, right? It never stops. And that's usually not a problem because it's decaying to 0 pretty quickly out in the tails, right? But what if you exponentiate those tails? The left tail is going to disappear because it'll just show up over here. But the right tail, it's as though you've taken the right tail and exaggerated it because you took it and exponentiated it. And so the log normal distribution has an embarrassingly long right-hand tail. And the result is that when you do Bayesian inference, you get intervals that are correctly calibrated, but the mean length is enormous. Even the median length is enormous here because the mean became so much bigger because every now and then you get a really, really big observation from the log normal. And look, it does a pretty good job of balancing it, 90% in the middle and about 5% in each tail. So this is a Bayesian solution to this problem, but it's one in which we end up, the only way we can solve it is we have to guess somehow. It's like the game with the Wizard of Oz. We have to guess that the wizard is generating log normal data behind the green curtain, and then we'll get the right answer. But parametric Bayesian inference based on log normal, the log normal distribution is horribly non-robust. Here what happens is I told the Bayesian machinery that the data were log normal when actually they were normal. And look, with 500 observations, 90% intervals are covering 85% of the time, but with only 10 observations, the Bayesian intervals are covering never. And with 50 observations, they're covering only 44% of the time. The same would be true, by the way, of the frequentist intervals. If you tell the frequentist machinery that things are log normal, and then you feed it normal data that's very different from the log normal that it thinks of, the frequentist and the Bayesian methods are both going to be horribly non-robust. So we need to bring in the tail weight and the skewness non-parametrically. And so first of all, this master student and I tried an ad hoc method, which I'm not even going to tell about because it didn't work. And then here's a principled method that does actually work. And this is going to be a little unit on how Dirichlet process priors work. So to remove that ad hocery of the method I just said I wasn't even going to tell you because it doesn't belong there, I'm going to work with Bayesian non-parametrics now. I'm going to try to come up with a prior on the set of all CDFs. The first person to figure out how to do this sensibly was an old friend of mine named David Friedman, who used to be at Berkeley and unfortunately died a couple years ago. Friedman's work was part of the way to the full story, and the guy who really invented the Dirichlet processes is a great statistician who's still emeritus at UCLA named Tom Ferguson, and he did this work in the early 70s. So Friedman said, the natural thing to look at from the data, if you're trying to learn about a cumulative distribution function, capital F, is to look at the empirical cumulative distribution function, because that turns out to be very much the best estimate of the true CDF. Now, if you were to take IID samples from the empirical distribution, that's essentially what the bootstrap does. Remember, it takes IID samples from the data you have, and if I showed you the empirical CDF, you can reconstruct the data set from it, and if I showed you the data set, you can work out the empirical CDF. So they're identical information representations. So IID sampling from the empirical CDF just gives mass 1 over n on each of the n data points, and that's multinomial. Like I said before, we can sort the yi. There might be some ties in the y values, as there were over here in my little sketch. And so let's sort the yi's into k bins, where k is how many unique values there are, and k is some number less than or equal to n. And k, in fact, will be less than n if there are ties. Let's call the bins b1 through bk. And I'm just going to count now how many of the data points fell in bin j, bin bj. Then, to take a single draw y star from the empirical CDF, the sampling distribution of that is given by the multinomial distribution, which, if you haven't seen it lately, looks like this. You go theta 1 to the power n1, because n1 is the number of yi's in bin b1, and theta 2 to the power n2, down to theta k to the power nk. If you look at that for a minute, that's a lot like a generalization of the binomial, because we would have theta to the something times 1 minus theta to the other thing, right? That's how the binomial works. And the thing about these theta 1 through theta k's is that they are anything they want to be, except they all have to be positive and they have to add up to 1. So I could rewrite this as theta 1 to the power times theta, some power times theta 2 to another power, where theta 1 plus theta 2 equals 1, but that's the same way as what I've written it this way. So that's one way to write the so-called multinomial distribution. Now, does anybody remember what the conjugate prior was for the binomial distribution? Also the Bernoulli. Anybody recall? It was the beta family. And so if we're going to generalize the binomial to the multinomial to a multivariate generalization of the binomial, we need a multivariate generalization of the beta distribution. And that already exists. It's called the Dirichlet distribution. So the conjugate prior for the multinomial is this thing called the Dirichlet. And so here's how it works. To say that some quantity theta, which consists of a bunch of probabilities that add up to 1, all of which are less than or equal to, greater than or equal to 0, but they all add up to 1. To say that a vector of probabilities that adds up to 1 is a draw from a Dirichlet distribution with parameter alpha, where alpha is a vector, alpha 1 through alpha k, where all the alpha j's are strictly greater than or equal to 0, is to say that the sampling distribution of the theta has the same exact mathematical form as the sampling distribution of the multinomial when thought of as a function of theta. And in fact, looking at equation 7 and looking at equation 8, you see right away that you have conjugacy, because you remember what that means. The product of the prior times the sampling distribution is supposed to be of the same family as the prior. And look, if you multiply things of the form theta 1 to a positive power, down to theta k to a positive power, if you multiply two things like that together times each other, you get another thing of that same form. So this is sort of proof by inspection. We can see just by looking at it that the conjugate prior for the multinomial is the Dirichlet. And so now you're beginning to get a flavor of why this thing is called the Dirichlet process, because it's based on Dirichlet distributions. So Friedman said the following. Okay, so I'm going to draw a little bit over here on this page that you can't see deliberately, and then I'm going to turn the document camera on so you can see it. Take the number line, and I've done a little illustration here where k is 5. So here we have k equals 5. Make a random partition of the number line into 5 intervals. And the way you do that is you choose 4 cut points at random anywhere you want on the number line. And having chosen those 4 cut points, the left hand, the smallest one, defines an interval that starts there and goes down to minus infinity. The biggest one defines an interval that starts at that cut point there and goes up to plus infinity, and the other ones are all the intervals in between. By what I've done so far? Now, there is some density, little f, that I could plot over top of that. And having chosen a random partition, little f assigns a certain amount of probability to each of those partition sets. Here it looks like f assigns about maybe 0.4 right there, and 0.25 right there, and 0.2 right there. And what is that? 4, 6, 8, 0.85, 0.05 here, and 0.10, for example. So I have a particular f I'm thinking about. This is a density. And that density has CDF capital F that I'm trying to put a prior on. Then look, these 5 numbers, 0.2, 0.25, 0.4, 0.05, and 0.1, have to add up to 1. So that forms one of those vectors that behaves like a Dirichlet, because it's a vector of probabilities that have to add up to 1. So here was Friedman's definition. We're going to define a thing called a Dirichlet process, which is a generalization of the Dirichlet distribution. And I'm going to pick something called alpha, where alpha is itself a distribution. And I'm going to say that capital F is a draw from a Dirichlet process with parameter alpha, if and only if, for any partition of the real line, the random vector that I get by working out how much area there is in each of those partition sets follows a Dirichlet distribution, with parameter given by the amount of probability the thing called A, which is itself a density, assigns to each of those partition sets. So once again, I'm going to create a random probability story. Every time I draw from this process, the outcome is going to be a new density. By choosing a random partition, and it can have as many components as it wants, we're going to choose a particular set value like k. In fact, k can be anything it wants also, so we might let that vary as well. For any partition of the real line, which we obtain by picking k minus 1 cut points. So this is cut point 1, cut point 2, cut point 3, cut point 4. That partitions the real line into 5 sets. I make a random vector that consists of how much probability is in each of those little sets. And I force that little random vector to have a Dirichlet distribution, because it is a bunch of thetas that add up to 1, whose parameters depend upon the thing that I'm trying to focus upon. I didn't say that very clearly, and I'm going to try over lunch to figure out a clearer way to say it for you. But the upshot of what he just did was he essentially built upon the Dirichlet distribution to create something that had the following properties. Here's the way CDFs behave, right? They always live between 0 and 1, and they can't ever go negative, and they can't ever be bigger than 1, and they always have to go either stay flat or go up. So by this means, Friedman invented a way of sampling from a distribution in such a way that every point that came out of there was an entire cumulative distribution function. And in fact, it might have been a discrete one. I'm drawing it continuously, but really all these guys are going to be discrete CDFs. Because look, each of these things defines a CDF. You see that? The CDF that puts 0.2 of its mass over here, and so it goes along like this. Well, this is a CDF that's derived from this, and then it jumps up to 0.2, and then it goes along, and then it jumps up to 0.45, and so on. Basically, this is implying a CDF. And so every time I create a partition set, and I have a particular, this actually corresponds to the alpha, I guess, that we're talking about. Every time I write down a different partition set, I get a different CDF that comes out of it. And look, that's the way of making draws so that every single thing I get follows a CDF. Now, by the way, you'll notice by the way Friedman constructed it, the only possible draws that you could get out of it are discrete CDFs, because it's going to have a jump every time it reaches this new chunk of probability. And that was initially thought to be a terrible drawback of the Dirichlet story. And we're going to have to do something to fix that drawback, because if we try to use this story to model continuous data, it's going to fail, because always we're going to get out discrete draws when we're trying to model something continuous. So people have found it useful to express the alpha thing that we're working with in the following form: the product of two things, a number C times an underlying cumulative distribution function F0. And so what's happening here is something that I didn't focus on before, but in fact is generally true, namely the following. If you look back at all of the prior distributions we work with all quarter long, so we started with the beta, and then we talked about the gamma, and then we talked about the normal, and I guess those have been our main prior distributions. Sometimes we would write down an inverse gamma, and so on. So we've got all these different parametric priors. If you look back on them, the ones that have two parameters in them, and that's most of them, right? I guess except for the t distribution, which we never use as a prior. But anyway, all the simple distributions we use have two parameters in them, and those parameters can always be thought of as having the following interpretation. They can be reparameterized. The parameters don't always come in this form. Having the following two pieces of information. One is a prior estimate of the thing that the prior distribution is trying to summarize information about. And the other thing is something that acts like a prior sample size. You remember that diagram we had a while ago where the prior could be thought of as like a data set, having a certain number of observations in it. And then the posterior is something that you would get by merging the prior data set with the sample data set. And so there's two numbers that drive any of our basic priors in Bayesian statistics. One number that stands for the prior sample size, and the other one that stands for the prior estimate of the thing that's being given a prior distribution. And that's exactly what this Dirichlet thing does. The number C acts like a prior sample size, and the number F0 acts like a prior estimate or guess for what the actual CDF is that we're trying to sample from. And when you write it this way, you get, this is the thing that Friedman was trying for. When you have a conjugate prior, you remember, it always has the property that if you start with that prior in the prior distribution, the posterior will have the same form that the prior did. So here's Friedman wanting to put down this thing called a Dirichlet prior on capital F, and if he's done it correctly, then the posterior distribution has to be another Dirichlet process. And so now the only question becomes, what's the updating rule? And the updating rule is extremely simple. Right there, equation 9 at the bottom of page 10. It says if F is a draw from a Dirichlet process with sample size C and prior centering distribution F0, which acts like a prior guess for the underlying capital F, and if it's true that all the yi's given F are IID from F, then the posterior distribution for F given the data is going to be another Dirichlet process where C updates to C star and F updates to F star. And look how simple the updating is. C star is just equal to C plus N. In other words, posterior sample size is equal to prior sample size plus data sample size. And look what the F star is. How would you describe the F star? It's one of our favorite things. It's a weighted average of the prior guess, F0, and the empirical CDF, which is the data guess, with weights given by the prior sample size and the data sample size. Isn't that beautiful? So Friedman, I think Friedman was aiming for equation 9, and he worked backwards from equation 9 to work out what the process had to be in order that he achieved equation 9. I think that's what he did. And he's passed on now. I can't ask him, but I wish I had, because I'd be curious to see. So we've reached time for lunch. After lunch, I'm going to tell you a little bit more about this, and I'm going to show you some pictures which will bring the whole Dirichlet process to life for you, I hope. And again, I apologize for the last 15 minutes or so being a little bit more theoretical than we like, but we're headed towards something very useful. So let's pause for lunch and come back at 1:30. So VC Ops, we're going to shut down now for an hour and start up again at 1:30.